The topic of this lecture is series of functions. We'll cover these points in this lecture: pointwise convergence of series of function, uniform convergence of series of function, Weierstrass M-test, and a theorem. So let us see the definition. Pointwise convergence of series of function, that u1, u2, un be real valued functions on a set E, and we say series n is equal to 1 to infinity un converges to a function f on E if the sequence of function Sn converges to f on E, where Sn is equal to u1, u2 up to un. In this case, we write summation n is equal to 1 to infinity un is equal to f. That is what are given: u1, u2, un are the functions, and from this we define, and so on. We define the function Sn, that is u1 plus u2 up to un, and if Sn converges to some function f on E, if it converges pointwise to E, then we say the series un converges to f pointwise, and we write like this way. And if this series Sn converges to f uniformly, then we say this series converges to f uniformly. So that is the only definition of this. The second definition, that is the converges uniform. When this converges uniform, if this Sn converges to f uniformly, this Sn converges to f uniformly, then we say the series n is equal to 1 to infinity un converges to f uniformly. Now let us see a theorem which is called Weierstrass M-test. It says that if summation uk be a series of real valued function on a set E, and if there exist positive numbers m1, m2, m3 and so on, such that series k is equal to 1 to infinity mk is less than infinity, that is, this series is convergent, and modulus of ukx is less than equal to mk for all k and for all x belongs to E, then this series uk converges uniformly on E. That is, if these conditions are satisfied, then this series converges uniformly on E. So let us see the proof. As series uk is dominated by this series, it means this condition holds, these two conditions holds, this one and this one. So this implies there exists n1 such that for all k greater than equal to n1, modulus of uk is less than mk for all x belongs to E, and x is greater than n1. Now let as Sn is equal to u1, u2 up to un, and Tn is summation k is equal to 1 to n, mk, that is m1, m2 up to mn. Then for mn greater than equal to n1, we have modulus of smx minus snx, that is modulus of summation k is equal to n plus 1 to m ukx, that will be less than equal to summation k is equal to n plus 1 to m modulus ukx, that will be less than equal to k is equal to n plus 1 to m mk. That is because ukx is dominated by mk, and that is nothing but tm minus tn, that will hold for all x belongs to E. So finally we got from here that modulus smx minus snx is less than equal to tm minus tn. But as this series is convergent, it is given, so sequence of partial sums Tn is convergent sequence and a Cauchy sequence. Therefore, for given epsilon greater than 0, we can find a value n2 such that modulus of Tm minus Tn is less than epsilon whenever Mn is greater than n2. But by 1, we get that Smx minus Snx, which is less than, we have shown that it is less than Tm minus Tn, and this is less than epsilon, so this value is less than epsilon for all x belongs to E and Mn is greater than n2. But this implies that Snx converges uniformly on E by Cauchy criteria. So this implies UK converges uniformly on E. So by this way we have proved that UK converges uniformly on E. Now let us see the next theorem. It says that if the series k is equal to 1 to infinity uk be a series of function in RAB, that is each term is Riemann integrable which converges uniformly to a function f on AB, then resulting function f is also Riemann integrable, and integration a to b fx dx is equal to summation k is equal to 1 to infinity integration a to b ukx dx. It means that if these conditions are holds, then we can interchange the series and the integration sign. That is integration a to b summation k is equal to 1 to infinity ukx dx. This will be same as summation k is equal to 1 to infinity integration a to b ukx dx. So let us see the proof. Let Sn is equal to u1, u2, un. Then Sn is Riemann integrable. Why this is Riemann integrable? Because each uk is Riemann integrable. So Sn is Riemann integrable. And as Sn converges uniformly to S. How this happens? Because we are given this series is uniformly convergent to F. So Sn converges uniformly to F. Therefore, F is also Riemann integrable. And when we find the limit n tends to infinity a to b Sn x dx, then it will be a to b fx dx because Sn converges to f uniformly. So this is permissible. But a to b Sn x dx is a to b, and we put the value of Sn x over here. We separate the integration in this form. We get summation k is equal to 1 to n a to b ukx dx. So this result we obtained that this integration is equal to this. Hence, when we take limit n tends to infinity a to b Sn x dx, that will be limit n tends to infinity summation k is equal to 1 to n a to b uk x dx. That will be summation k is equal to 1 to infinity a to b uk x dx. This is 2. So by 1 and 2, this is number 2. We have obtained this. And what is 1? So let us see, the 1 is given over here as this result we have seen. So because of this 1 and 2, we got that integration a to b fx dx is summation k is equal to 1 to infinity a to b ukx dx. So by this way, this proof is complete. Here note that this thing is important. So whenever in some numerical problems also this things comes, then this integration can be taken inside and can be solved. So this is the importance of this theorem. So thank you very much. You can find the link of this PPT in description box. Thank you very